Ultimately, we would like to describe realistic processes like the collision of electron-positron and producing a muon and antimuon. However, this is made quite complicated because of the spin of the particles. So let's start first with scalar fields, and we can replace the fermionic field by a field small phi and the bosonic mediator by a scalar field big phi. However, again, that's two fields which we can reduce using effective field theory in the case where big phi is very heavy to a phi-4 theory where we have only one real scalar field. The phi-4 term is an interaction term, therefore we expect that it will allow us to describe collisions between incoming disturbance of the field which then change their momenta. Our path integral gives an amplitude of probability for the field to go from vacuum to vacuum under some given setup of sources J chosen by the physicist. And we hope that with a good choice, a clever choice of sources, we will be able to describe such a collision process. But because we don't know how to solve this path integral, we have rewritten it in a different form involving an exponential of functional derivatives. That's not a solution to the path integral. This is just a different formulation which has the advantage to have no path integral in it anymore, and which is useful in perturbation theory. So in particular when lambda is small enough that we can take a Taylor expansion of this exponential. To have the collision amplitude encoded into the path integral, we need to make sure that the sources create the initial disturbance of the field, because before that we want to be in the vacuum. And we also want sources playing the role of sinks, annihilating the final disturbance of the field after the collision. This means we have a sum of 4 sources, so we are only interested in the J4 term of this expansion. All the other terms in J0, J2, J6, etc., which are contained into Z, are not relevant for the physical process we are interested in, so we need only to extract what we want from this big path integral. And that's why we Taylor expand the second exponential in order to keep only the power in J which are relevant for our case. And we also consider the case of lambda being small, therefore we can use a perturbation theory, and in fact we are going to do the calculation only for the first order in lambda. We saw in the baby problem that in order to get a lambda J4 term, we take the first order of the first exponential and the fourth order of the second exponential. As we have two space-time integral in the exponent, when we take the fourth order of the Taylor expansion, we end up with 8 integrals over space-time. And similarly, we have 4 propagators, because there is only 1D, and 8 sources, because there is 2 of them in the initial exponent. Because of the first exponential, we have 4 functional derivatives. A functional derivative is a derivative with respect to a function evaluated at a given value of its parameter x. We can see it as a problem where we have an infinite number of variables. Each f of x corresponds to one variable, and if we have an infinite values for x, we have an infinite variables f of x. We are only deriving with respect to one of these variables, so to f of x. This means, for instance, that if we apply this functional derivative to f of y, we get a delta function, because f of y is not the same variable as f of x, so it's usually 0, except in the case where y is equal to x. You can see more about functional derivative in Lancaster and Blundel's book. However, that's the only property we are going to use in this course. So we see that the 4 functional derivatives, when they act on the sources, are going to introduce 4 delta functions. And in particular, we are going to be left with only 4 of the initial 8 sources and 4 of the integrals. So because we will end up with only 4 sources, that's what we expected, because we are going for an amplitude which is in lambda j4. So all we have to do for the moment is to convert 4 of the 8 spacetime variables into W's. But in doing that, we will recognize 3 different type of terms. But these terms do not necessarily describe the same kind of physics or the same process. So if we look, for instance, at the space-time representation of the first term, we see that the first propagator propagates a disturbance of the field from W to W. So does the second propagator, while the last two propagators propagate disturbance of the field between the sources. Similarly, for the second term we have, and for the third term, the physics associated with each of these terms is different. In the first one, we have particles which propagate freely between the sources, and on top of that we have a fluctuation of the vacuum. So the interaction is making the vacuum fluctuate and creating virtual particles at a given point of space-time W. In the second one particles propagate freely and the second one interact with a virtual particle of the vacuum. Only the last term corresponds really to a collision between two incoming disturbances of the field, which collide at a given point of space-time W and then propagate with different energy momenta to the sources in B and D. So when we apply our functional derivatives to the source terms, we only keep the terms which will correspond to this term associated to a collision. That means that whenever one of the variables, the space-time coordinate, has been transformed into a W, the other one associated with this W should be left unchanged and should not be acted upon by a functional derivative. So let's rewrite this term and expanding all the indices. So the first functional derivative can act on any of the 8 sources, and it doesn't matter which one we choose because it will produce 8 identical terms, so we have a factor of 8, and we make it act on the last variable. The second functional derivative can act on any of the first 6 sources because we don't want to produce a dWW term. The third derivative can act on any of the 4 first sources, and there is 2 choices for the last derivative. This gives an amplitude which has only 4 sources left. At this stage, that's when we want to make a specific choice for the sources in order to be able to solve the remaining integrals. And of course we made our sources act on some position of space-time, and the simplest choice is then to choose delta functions. Each of the integrals over x, a, x, b, x, c, x, d is going to be killed by a delta function. However, we see that we have 4 possibilities for each variable. For xa, it could be killed in x1, x2, x3, or x4. And same thing for all the other variables. However, again, not all possibilities is going to be physically associated with the amplitude we want to calculate. So let's start with xa. In that case, it doesn't matter which delta function kills the integral, so we have 4 possibilities which are going to be equivalent. For the second integral on xb, we expect to have again 4 possibilities. However, if we choose x1, then we will end up with a diagram which has 2 disturbances of the field excited at the same source in x1. And of course we don't want that because that means we don't have anything to annihilate in x4. So we are not looking at a problem where we create 3 disturbances of the field and only annihilate one. We want to have a collision where two incoming disturbances of the field collide in W and then scatter and are annihilated later in X3 and X4. So that means there is only three choices for XB because I have already chosen X1 for XA. And similarly for the last two integrals. So this gives us a 4 factorial term which cancels with the 4 factorial in the denominator. And that's why we wrote lambda and 4 factorial in the Lagrangian. That was a convenient choice because we already knew that it was going to be cancelled by this term. So we end up with a product of 4 propagators between the sources and the interaction point. Now it's time to replace this propagator by their explicit expression. A note about convention: we can choose a sign in front of the exponent because we are integrating over all momenta from minus infinity to infinity. And by convention we choose a minus sign for an incoming particle and a plus sign for an outgoing particle. If we isolate all the terms with W, we recognize a delta function, which tells us that energy and Euclidean momenta are conserved. So we are left with the integral over k1, k2, k3, k4, and this can be written in terms of a Fourier transform of the amplitude of probability itself. In fact, that's really the Fourier transform of the amplitude we are interested in, because in any experimental setup we usually know what are the energy and momenta of the incoming and outgoing particles. The delta function is here because of energy momentum conservation, and apart from students in an exam situation, nobody is silly enough to calculate an amplitude of probability for a process which does not conserve energy and momentum. Therefore, it is understood that this term is always here and we don't write it explicitly. The last four terms are the propagators for free particles in momentum space. We don't need to have them because they are not contributing explicitly to the collision amplitude. They are just here to bring the particles into the interaction point in space-time. So our final amplitude in momentum space for the collision in first order in lambda is only just minus I lambda. Although the result is simple, it took us quite some time to get there. Feynman introduced his rules and in particular the Feynman diagrams in order to make the process for such calculations much simpler. Indeed, if you repeat the calculation for different orders or different number of sources, you will recognize some patterns which are systematic and always depend just on the number of sources and the order of the interaction. And therefore that makes all this diagrammatic technique introduced by Feynman very powerful and very systematic. And we are going to use that from now on.